In this video, we'll cover complex ion formation. In a complex ion formation, it's just as it is, says it is a formation of this very complex looking ion, and it's made up of usually a central transitional metal ion, like this one it's be silver, and then you have a surrounding molecule or ions. This surrounding molecule will be ammonia. There's something missing over here. I think this should be +2. Okay, so now that we have this particular complex ion formation, we could write a chemical equation how this molecule, this large molecule, is formed, and that's by this equation here. And you see the silver and ammonia forming into silver connected with ammonia. It has got a charge of +2. And notice that there's an equilibrium sign, and hence why we are talking about the complex ion formation at equilibrium. So this Kf is the equilibrium expression for the complex formation. So what is the Kf expression for complex ion, in this case the silver and ammonia? So we can write Kf is equal to, just like we did for Ka and Kb and Ksp, we write the product first, the concentration of the product first, and then we divide it by the reactant, and making sure that all the coefficients of the reactions are included. So since this is 2, I'm going to write to the power of 2. Now let's go into what sort of more complex ion formation can you see in this particular table. So here's silver cyanide. Getting silver and the 2 cyanide forming silver cyanide ion. Complex ion, you have copper, you have iron. So this table is in your reference sheet, and it will be tested on one of these chemical equation, and I won't go outside of this particular chemical equation. And all the Kf values, or the equilibrium values, is here. Now note that this is a very large value, so the Kf value is quite large. And the large value indicates that this will go almost into completion, meaning that it will form a lot of this complex ion and very little of the reactants. Okay, big complex ion and little of the reactants. I want to review some of all of the K equilibrium expression we have covered so far, just in brief, just to get to the point of the equilibrium constant for formation. This will be, I hope, the last one for you. And so equilibrium constant for chemical reaction, where we had A and B form into C and D, we were able to write the equation like this. As long as they were in aqueous or gas, none of the liquid and solid were included. Also, we carefully selected the coefficient of the reaction and put them as exponents. And that applied for the Ka and the Kb. The only difference is now you have a Ka value and you have a Kb value. A lot of the times for acid and base equilibrium reaction, we had water involved, and water was not expressed in the equilibrium constant expression equation because it was in liquid. What about for formation of a solid, the Ksp? So here's my solid going into aqueous form, or reverse would be formation of the solid. So if I were to write a Ksp, I only included the aqueous, and you'll notice that there's no denominator or the bottom because the reactant in itself is a solid. So this shows the equilibrium constant of that solid dissociating in water. And finally, we come with the equilibrium constant for a complex ion, the formation of it. So here's a metal ion probably with its coefficient, and N representing coefficient for Y. Maybe a ligand molecule could be like NH3 we just talked about. The other one was cyanide. It could be even a charged particle. Nevertheless, you form this complex ion. And so we are able to put this KF values, this should be KF value, and that gives me the product over reactant, and the product has also a coefficient with P, and the reactant has coefficient for N, M, and N accordingly. So this is the portion that we're going to be focusing on when we're talking about the complex ion formation. Now let's do a learning check based on what we have learned so far. What is a concentration of silver in a solution made of 20.0 milliliters, 0.01 molarity of silver nitrate, and 5.0 milliliters of 18 molarity of ammonia? So here we want to first take out the spectator ion, and I can see that nitrate is a spectator ion. Then we look at, okay, well, how is this going to form a complex ion? We have silver, we have ammonia. Well, what does it form? Based on this table, it tells you exactly what it forms, and it forms into silver, NH3, to plus. Oh, it is a plus. And there's a 2 coefficient in the beginning. Okay, let me write a plus sign here. All right, here you'll notice that we have this equation, and we're going to be utilizing the ICF table. And the reason why we use the ICF table is because we want to work with millimoles, and second is because it's as if it's going all the way to completion. So if you look at the KF values is quite high. So in fact, all of these are really, really high. Okay, now let's go ahead and do the solve for millimoles for all of these guys. So initially we had 20.0 ml of silver. So I'm talking about silver over here. And if I were to multiply by its concentration, which is moles over liter, and we cancel out the liter, I would get 0.20 millimoles of silver. Now let's do that for ammonia as well. So we have 5.0 milliliter times 18 moles over liter. We cancel out the liter. So go ahead and punch this into the calculator, and you should get 90 millimoles. So let's plug this in, 0.20, this would be 90. And then we don't have any of the silver ammonia, the ion complex ion formed yet. So now we're going to go through change. The reaction is going to start going. We look at the limiting reagent, which is the silver, because that's the lowest value. You subtract it by the lowest value. And on the right side, we add it by its subtracted value. So it's plus 0.20. What about here? Well, you'll notice that there's a coefficient of 2. And so if there's a coefficient of 2, then we need to write it's 2 times what was originally the limiting reagent. And then we'll go ahead and add the I and the C value together and see what we come up with final. So here it's 0. This one would be 89.6. And then this one would be plus 0.20. And these are all in millimoles. Okay. And then we're going to go ahead and find out the concentration of all of these guys next. Okay. So we're going to find the concentration of this one. So if I want to know that, I need to divide it by the total number of volume, and that's T total volume is equal to 20.0 plus the 5. It's 25.0 milliliters. So here, 25.0 milliliters, and then this is 25.0 milliliters. All right, I can't do this on my head, so we'll go ahead and I'm going to punch out a calculator. That's 89.6 divided by 25.0. So that's 3.58. What about that one? Point 2 divided by 25. It's 0.00800. Molarity of the AgNH3 2 plus, and this one would be for ammonium. Now look at what the question is asking. It's asking for the concentration of silver. So you'll notice here it's like, okay, well, everything went out, so there's no silver. But remember how I mentioned that these are all in equilibrium. So I know that most of them goes towards the right, but there's going to be very, very teeny tiny leftover of the silver. So we'll go ahead and write the KF expression. So this IC, first you do the ICF table, and the second step is to do the KF expression. And we have the product all over the reactant, silver, and we have NH3 to the second power. All right, we do have values for everything except for silver because that's what we're looking for. So we're going to go ahead and multiply silver both sides. So that's going to get rid of the silver here. And then I'm going to go ahead and divide KF. So I'm going to go ahead and divide KF. So that's going to go on the bottom here, KF. And that will get rid of the KF here. Okay, so let's write this down. Silver concentration is equal to the concentration of the ammonia, the ion, complex ions, all over ammonium to the second power and the KF. So if I were to actually put in the values, I would write 0.0080. And this would be 3.58 to the second power, and the KF value is 1.7 times 10 to the 7th power. That's written right here. So let's plug this in. Divided by 3.58 to the second power. Okay, I'm going to put that as enter for now. And then divide that again by the 1.7, the KF value. And let's double check my key and what I have written down here, which is 3.67. So it's about 3.7. Okay, 3.7 times 10 to the negative 11 molarity of silver. So this would be very, very small value of silver left over. So it's pretty much like it went into completion. But if you really want to know that trace amount, then here it is, okay? Let's do another learning check. If 0.0846 molarity of copper nitrate is added to 500 milliliters of 1.0 molarity aqueous ammonia, what is the equilibrium concentration of copper ion? So same thing, we're going to go ahead and take out the spectator ion and add copper plus ammonia. I'm going to find this something like this on this chart, and I see it right here. And that takes 4 ammonia. And then this goes into forming copper NH3, 4, and 2 plus. How do I know that? That's written all here, okay? All right. And then we're going to do the ICF table. So you're going to try the ICF table. You don't need to use millimoles this time because they're both in molarities. And so try it in molarities and then come back and check this video. And here is the key.